Dr. Tessmer continued postdoctoral research at Massachusetts Institute of Technology from 1996 to 1997. Dr. Tessmer's research group at MSU now develops and applies scanning probe microscopy to study the behavior of charges on nanometer length scales. Dr. has won several awards and recognitions, including Undergraduate Merit Scholarship of the University of Washington in 1986, the National Science Foundation Fellowship Honorable Mention in 1990, the Alfred P. Sloan Research Fellowship in 2000, the Thomas H. Osgood Award for Excellence in Teaching in 2001, and the College of Natural Science Teacher Scholar Award in 2004. Dr. Tessmer has been actively associated with Dalbagh Educational Institute very recently when he delivered a research talk through video conferencing between MSU and DEI. I now invite Dr. Stuart Tessmer to please deliver his talk.
Thank you for that nice introduction. And in fact, I think that it was even more elaborate than what I'd sent in email. So someone looked at my CV to make it more elaborate. So thank you very much. Just to totally throw everyone out of whack, I'm going to start on this side and thank the first two speakers for actually really providing a wonderful overview of this field of nanotechnology and nanocomputing. And in particular, if this chalkboard works, I would like to draw a graph that I'm going to reproduce directly from Professor Kumar's talk as an introduction or as motivation for my talk. So he was applied, I'll call this a semiconductor computing. Thank you for the lights. And he gave us many interesting things in his talk. One of them was a plot, the number of atoms per bit used in a modern computer. Now this axis was time. And I'm going to get all the numbers not right, so I'll, bear with me on that. But down here at the bottom, we'll put 1 atom per bit. At the top here was something like 10 to the 20 atoms per bit. And on an exponential graph, there are many decades in between. We'll start here in 1970. This is just approximate. 2008. And then right here, 2035. And the data points look something like this. So I have to do, so it's something like 10 to the 3 right now. And then an interesting extrapolation is if you go to 2035, I'll put in red, that's when you get to 1 atom per bit. So that makes me feel great because that means we have about 30 years for the kind of experiment that I'm doing to actually produce a functional device. But this is what we're interested in. We're interested in what can you do with truly single atoms inside of semiconductors. And as you'll see, this talk uses the most basic quantum mechanics. We're very far from doing anything like actually manipulating the spin and building a device that is well controlled. But you have to start from somewhere. So I will show you the results of our progress, and hopefully some of it will make sense to you. And now I'll go to that side. This works. All right, so here's the title of my talk, Scanning Probe Spectroscopy of Semiconductor Dopant Molecules. So a dopant is when you have 2 individual donor or acceptor atoms, and if they're close enough together so that interaction is important, then you can consider it a molecule. And at some level of my talk, we're interested in that as well. It's a scanning probe technique. There's a tip, there's a sample. Individual dopants are somewhere inside the sample. Several times through this talk, you will be thinking, this looks like STM, scanning tunneling microscopy. That's where you have a tip, you have a sample, you have charge tunneling onto the tip. I'm sure most people in this room have heard of scanning tunneling microscopy. Why do I make a big deal of it now? It's because that's not what I'm talking about. It looks so much like scanning tunneling microscopy, but it's not quite the same. The charge is moving, but it's always moving inside the sample, and it's never tunneling onto the tip. I hope that'll be clear as I continue. To give credit to the people that did the hard work, 3 graduate students, Irma Kuljanishvili, Morwell Geseller, Jamil Kayesh, Michigan State University. Here are our sample growers, Lauren Pfeiffer and Ken West at Bell Labs, and Lou and K-Max at IMEC in Belgium. These are all the theorists that helped us understand the work. Oops, that's me, I'm not a theorist. These other 3 gentlemen, Jim Harrison, Tom Kaplan, and Carlo Pierre Marocchi, played key role to help us understand what we're doing. Here's an overview of the talk. So, what is a dopant? A dopant is an impurity atom inside of a material made of something else. So if we have some nice lattice of material, for example, this could be silicon, somewhere the person that grew the silicon managed to put a substitution. If it's a boron or a phosphorus atom, it'll go in as a donor or an acceptor of an electron. So this is a foreign atom sitting inside of a nice lattice where everything else is uniform. In the case of a donor, it's called a donor because it can give up an electron, lose an electron. If it loses an electron, its charge isn't neutral anymore. It sits there like a little positive charge. And in some approximation, you can in fact consider this to act like a hydrogen atom. It has 1 extra proton compared to the electrons. And so at a very simple approximation, you can say, well, it's like 1 proton. And so our method is to use a tip, some sort of sharp tip, to look at electrons or holes going on and off of these dopant atoms and see if we can say something about the quantum mechanics of the structure. That's the whole goal of this experiment. So let me suppose I'm trying to push a charge onto my atom. There's my charge, and I'm giving it a little push. I'm getting closer. If it sticks, if it's bound, then it'll stay there. And if that happens, I don't know if you noticed, but I also drew a little image charge appearing on the tip. Oops, wrong way. So right when it goes on, an image charge appears on the tip, and we have some way to measure that. This is exactly like a capacitor, where the atom, or the dopant, was 1 plate of the capacitor. The tip is the other plate of the capacitor. If you put more charge here, the push, of course, is a voltage. If you manage to put charge on the dopant, image charge is induced on the tip. So the charge doesn't jump to the tip. It actually doesn't do anything except for to go back and forth somewhere inside the sample. But the image charge that's induced on the tip, of course, is due to the electric field, as we all learned in our introductory electronics course. We're really looking at the electric field coming out of the sample and the resulting image charge on the tip. And for that reason, it's ultimately a capacitance measurement. The important thing is the amount of charge induced on the tip compared to the push. The push is what I call the excitation voltage. The typical units are 10 to the minus 18 coulombs per volt, which is an attofarad. 1 attofarad is sort of the typical capacitance unit that we end up dealing with. As you can see, we call this charge accumulation imaging. All right, so that was my overview of the talk. So now this is the rest of it. I will give some more motivation. I really don't have to give any motivation based on the 2 talks that we've already heard today, so I'll go through that quickly. Then there's 2 basic physics ideas, Kohn-Ledinger and Lieb. It'll take me about 5 minutes or so to talk about these 2 things. I hope you don't fall asleep at that point, because if you stay awake enough to get the main idea, then the rest of my talk will make a lot of sense to you. So the motivation, here's a FinFET like we saw earlier today in Professor Kumar's talk. It's quite clear that device sizes are getting smaller and smaller. Understanding the role of small numbers of atoms inside semiconductors is crucial. Quantum computing or conventional computing, either way you look at it, we need to understand what happens when you have 1 or a few number of dopants. Also, basic physics is another motivation. It turns out, as I mentioned briefly, that the dopant, the donor or acceptor, is somewhat analogous to a hydrogen atom. So you can say that the experiments that we do has some relationship to atoms in free space. And that analogy actually can allow you to test some basic ideas of quantum mechanics. So here are the 2 important ideas I want you to stay awake for. Then I'll give you permission and you can all fall asleep. All right, the Kohn-Ledinger picture That is an approximation, very famous, made decades ago, of how to treat a donor or an acceptor in an impurity atom inside of a large superconductor. The end result is that you can consider an ionized donor acceptor like a hydrogen atom. And so what I've drawn here are these potential wells that go like 1 over R. That's the attraction, of course, of a charge of an electron to a proton. As you get closer, the force gets greater and greater, or it wants to fall into the well. And so if you consider that our sample has many dopants inside of it, it's like we have many potential wells that want to attract electrons. And that's what I've drawn here schematically. And there's my tip that we want to use to look at that system. So here is a better treatment of it. So it's also called the effective mass approximation, or Cone-Ledinger cone. Here it is, 1955. It turns out that this paper was written at the University of Michigan in Ann Arbor. Not where I'm from Michigan State, but very close, in 1955. The idea is that you have this ionized object, this donor inside of a semiconductor. It's given up 1 electron. You then ignore everything else about it, and you say, well, it has 1 more proton than an electron. Sure, it has a nucleus. It has lots of other electrons in there. We'll ignore all that and say, well, at some level, it's just like a single proton. You also ignore the lattice of all the other atoms around you, and you say, well, it's in a semiconductor. A semiconductor has a dielectric constant kappa. It has an effective mass for electrons. And if I just remember those 2 things, I can forget about the rest of the semiconductor as well. And so that's the picture. You end up with a 1 over R potential. You have to rescale the Bohr radius. So that's the average size of the electron that can get trapped in this potential. You rescale it by these 2 things, the effective mass and the dielectric constant. And you end up rescaling the Rydberg energy. That's the binding energy of the electron once it goes back on. I'm sure many of you remember from your elementary particle class that a binding energy of an electron in a natural hydrogen atom is, 1.36 electron volts? So that's the usual Rydberg. R star, in our case, the effective Rydberg is usually about 5 millivolts. So the electron onto these donors or acceptors, I have to say a hole bound to an acceptor, or an electron bound to a donor, is very weakly bound, only 5 millivolts or so. And it's very much spread out. This parameter of the Bohr radius ends up being on the order of 5 or 10 nanometers, or at least 2 nanometers. So many lattice sites. And that, if you remember my schematic from earlier, I drew the electron really spread out on top of that plus sign. We can go a bit deeper. This is the Hamiltonian for an electron bound to a hydrogen atom. This is just the time-independent Schrodinger equation. There's the kinetic energy term, potential energy term. If you apply a magnetic field, you get interesting effects as well. The magnetic field classically tends to localize an electron. An electron, of course, will orbit if there's an electric field present, classically. Quantum mechanically, the wave function gets squeezed in, and that changes the ground state energy, and that's actually seen here in this term. As you squeeze more and more and more, you're pushing the electron closer to that positive proton in the middle, and it turns out in this system, overall, that lowers the energy. Very different from quantum dots. When you don't have that positive proton in the middle, it's the opposite effect. This term ends up raising the energy, making the box smaller, and the levels get spread out more. Interestingly enough, for this atomic analogy, you end up with the energies getting smaller due to the magnetic field. This is the term that gives you the Zeeman effect that says the spin and angular momentum of the electron wants to be parallel to the magnetic field. All right, so that was number 1. That was the effective mass approximation. Is there a question? Please don't be shy. No? Okay. Big idea number 2 is Lieb's theorem. What is Lieb's theorem? It's a theorem, and it tells you about the maximum number of electrons that you can put on a molecule or an ion. It just gives you an upper bound, and it says that if you have some nucleus of charge Z, that the number of electrons that you can fit onto it is less than 2z plus 1. So I'm going to give you the simplest example possible, and that's a single proton, very relevant for the rest of the talk, by the way. And how many electrons can I push onto the proton? So I'll try to do that. Here comes electron number 1. I push on it. Will it stay? Will it be stuck? Yes, it'll be stuck. Of course it'll stay there because that's a hydrogen atom. Everyone knows an electron's very happy to be bound to a proton. Fine. That's not the end of the story. What happens if I try to push a second electron? It turns out it's bound as well. And you might not have guessed that. It's a polarization effect essentially. As you push it in, the charge cloud of the first electron wants to shift a little bit to the left, and that overall sees a little extra positive charge or a dipolar interaction which bounds the second electron. Interestingly enough, the quantum solution of this problem is spherically symmetric, although my schematic, I don't know how to draw it any other way than this. So that is it's bound, and in fact, a donor inside of a semiconductor does exactly the same thing. If you have an isolated phosphorus donor inside of silicon, you can put 2 electrons onto it, and that's called the D- state. How about a third electron? Well, Lieb's theorem says 2z plus 1. If z is 1 because I have 1 proton, 2z plus 1 is 3. It says the number of electrons must be less than 3. Therefore, if Lieb's theorem is correct, I cannot push the third electron on. So I'll try, and it won't go, not just because of Lieb's theorem, but because experiments show that as well. You cannot fit 3 electrons onto a hydrogen atom, and for that matter, you cannot fit 3 electrons onto a donor in most semiconductors. An isolated donor or an isolated acceptor will not hold 3 holes. It does work. And here's the reference for Lieb's theorem. So I've just referenced 2 very ancient papers. This is a perfect time for me to stop for a second. So I'm going to start talking more about the details of our experiment, but I've been talking already now for 15 minutes or so, so please ask a question. All right, I'll keep going. So now I'll spend a few minutes, 5 minutes or so, talking about our scan probe method. So you've already seen this schematic. It's basically a capacitor. We have a sharp tip, a sample. We're looking at the electric field coming out of the sample. Here's a schematic. I haven't made this point yet, but it's an AC measurement. Our charge detector, it's a transistor. It's a cryogenic transistor, a little bit like a single electron transistor, connected directly to the tip. And it gets a great sensitivity of 0.01 electrons per root hertz. We can see less than 1 electron on the end of the tip. But it's AC. You have to have some sine wave attached to your sample so that the charge is continually tunneling back and forth onto your dopant in question. The electric field, therefore, modulates up, down, up, down, up, down, and that gives us our signal. And it's easy for me to go on this talk and forget to mention an important point. It must be an AC measurement. Actually, this is to give proper credit to my advisor at MIT, Ray Ashuri. He actually developed a similar technique. He invented this charge sensor circuit and used it to look at electrons going onto quantum dots. The wonderful experiments that he did. In that case, the top was a gate electrode that was fabricated on top of the quantum dot. It was sitting there. Our case, we have a gate electrode that's a tip that we can move around. So a very good way to describe this experiment is to say that it's a scanning probe version of Ray Ashuri's single electron capacitance microscopy experiments done in, it should be spectroscopy there, in the late 90s. In that case, he was looking at electrons going onto quantum dots. In our case, we're looking at electrons going onto, hopefully, small numbers of donor atoms, donor and acceptor atoms. Can we see a single electron going into our dopant? It turns out you can. The question is, how do you do it? This is like a little quantum box. It's like a little particle in the box. It has quantum levels. You need to have an electrode below it that's a degenerately doped semiconductor, perhaps, but something that acts like a good metal that has a nice Fermi level, or a nice chemical potential, you could say. When the Fermi level, or the chemical potential of this bottom electrode, lines up with one of the quantum levels inside of our dopant, that's when the charge can tunnel. It's just like usual idea, you need to have a state to go into. You can't tunnel if there's no state with the right energy. So when the Fermi level here lines up with your state there, yes, you can tunnel. Since we changed the Fermi level of this thing relative to this thing by applying this bias voltage, which I call VTIP. Once VTIP is just at the right value and the quantum state here aligns with the Fermi level here, then the electron can go, but then it comes right back again. Actually, because of the sinusoidal component, which is usually much smaller on the scale of millivolts, this is on the scale of volts, the electron then resonates back and forth. And that gives us our AC measurement that is the key for our measurement. You can look at this more carefully, and Professor Tom Kaplan wrote a wonderful paper on this. You know, actually the expectation value of the number of electrons on the dopant compared to the change in the chemical potential, that thing is proportional to the capacitance that we measure. And I'd be happy to talk more about that if there are questions. All right, so all I want you to get out of this cartoon is that we have some sort of quantum system like a proton. We can change the Fermi level of this box, of this particle in the box, relative to the chemical potential of the bottom electrode. And what happens when we do that? Probably the better way for me to do this cartoon is to draw the Fermi level here fixed and have the particle in the box moving up and down. That's probably the better way to explain what happens as we change the voltage here. But for convenience, of course, it's the same idea. If we'll keep the particle in the box fixed, then I'll have the chemical potential moving. That just means I'm ramping the voltage here. So as I do that, if I make the voltage here more positive, then I'm trying to pull an electron towards the dot. The chemical potential of the bottom layer is getting closer and closer to the first quantum state. Ah, there it is. That's the first electron going onto our proton. At that moment, we have charge resonating back and forth. At that moment, we have image charge going on the tip, and then there's electron is just starting to enter onto our proton. Interesting enough, as I make the voltage a little bit higher, this electron's still sitting there, but our signal goes to 0 because it's not resonating anymore. It's just sitting there. We need something moving to get a signal. So nothing happens as far as our measurement's concerned until the Fermi level gets up to here, and that's when the second electron starts resonating back and forth. Now if we make the voltage a little bit higher, it's just sitting there, and we have no signal. So you see what our measurement is actually is a series of peaks. We get a peak when an electron can go on, or if an electron can go off. If charge is moving, we get a peak. And what can we do next? Oops, this is later. Okay. Here's some more details about our apparatus. This is an actual picture of the microscope. It's a Basaki design microscope for those of you that know about STM. The sample sits on a disk right here. There's a tip. Our cryogenic charge sensor, our transistor, is carefully mounted directly to the tip. Gets this nice sensitivity. It is constructed of 2 high electron mobility transistors. And that is really all I wanted to say. But if there are questions afterwards, I'd be happy to give you more details on how this works. Ultimately, in the end, we can see a very small number of electrons induced onto our tip. This needs to be a low-temperature experiment. It turns out, I've already mentioned, the quantum level spacing is set by the effect of Rydberg. That's only 5 millivolts. This experiment won't work at room temperature. You need to be cold. So our apparatus is a helium-3 refrigerator. The microscope's on the end of a long stick. Goes into the apparatus. It gets up actually immersed. The tip and sample end up directly immersed in helium-3. And we get this low temperature. For the data I'll show you, some of it was taken at 0.3 Kelvin and some of it at 4.2 Kelvin. Okay, my next couple slides, I'll show you the samples, and then I'll finally get to the data. So sample number 1 is a silicon sample doped with boron. It's pure doped substrate, which is what we need. Then it just has pure silicon with no impurities, we hope. Then somewhere in the middle of this there's a layer where boron was introduced, and we want all that boron to be in the same plane. Within the plane, within the XY plane, the boron is randomly positioned. Ultimately, of course, what we want to do is experiments where we really build devices where we have regular arrays or patterns of dopants where we can perhaps make a line of dopants or 2 dopants separated far from their neighbors. That's certainly the future where we want this experiment to go. But at the moment, we're using what we can get without killing ourselves, and that is a random array of dopants, a random distribution of dopants. On average in this sample, they're about 25 nanometers apart, which is great because the spatial resolution of this technique is about 25 nanometers. Actually, in this case, it's about 15 nanometers. Depends on how far this dopant layer is from the surface. If you're trying to probe something that's far away from your tip, you don't get very good spatial resolution. STM gets great spatial resolution, but the tip is right on the surface. It's looking at the atoms on the surface. In this case, the atoms are below the surface. A dopant or acceptor or donor isn't going to act in a nice way if we put it on the surface of the semiconductor. It has to be within the bulk. So the thing that we're trying to look at is about 15 nanometers away, and that means that the lateral resolution or the sideways resolution is also about 15 nanometers. We cannot see angstroms like you can with STM. So that is fortunate. This is a conduction band profile. So what we're doing actually when we tunnel electrons into one of these, boron goes in as an acceptor. I should say when we tunnel a hole into an acceptor, don't get worried. A hole going into the acceptor is exactly like an electron going out of the acceptor. Everything I told you is still true. And fortunately, also, this sample is very well characterized by Sven Roge's group in the Netherlands. We know that we have one state that's empty. It's called the E+ state, and it's about 6 millivolts below the top of the valence band. So we know about what energy the electron is supposed to be at. Here is a Sims profile of the sample. That was sample number 1. Sample number 2 is gallium-arsenide. And as you see, after I talk about sample number 1, you'll see that it's advantageous to try to get the dopants closer together. And in this sample, the dopants are closer together. On average, they're only about 9 nanometers. Also, the effective Bohr radius in this sample is larger, which means that interactions are more important in this sample. That is the reason I'm going to talk about it. The first level of the experiment doesn't say much about interactions, and if we want to do something at least slightly interesting, we could ask, how does the quantum level structure change as your distance to your nearest neighbor changes? That is certainly something you can control with lithography in the future. So we're trying to comment on interactions with nearest neighbors, and it's advantageous that this sample has the neighbors closer together. The big disadvantage is the delta layer is farther away, so that our spatial resolution in this sample is about 60 nanometers. So wherever we put the tip, we're averaging over a big circle. In this sample, we can't see one donor at a time because of that. The interactions are more important, but unfortunately, the dopants are so close together, we're seeing bunches of dopants and not one dopant. All right, if you want more details about this picture, I'd be glad to give it to you. Basically, all you need to know, though, is that we have a beautiful substrate layer called the two-dimensional electron system, from which we'll be tunneling into the donor layer. And the sample is a really good sample in terms of the quality and the purity. All right, finally, and thank you for your patience, I'm now well into my talk. I will show you some measurements. First measurement, not surprisingly, is on sample number 1. So this was the boron-doped silicon sample. If we put the tip in a lucky place and ramp the voltage V-tip and look at this capacitance signal as we ramp the voltage, we always see about the same thing. And that's a nice peak occurring around 500 millivolts, and then sort of a step-like feature that occurs at a higher voltage. This step-like feature I'm not going to talk about. We're glad it's there. It's something that we expected to be there. That's when an accumulation layer forms at the surface of the semiconductor. If you pull charges a lot, it turns out charges will get trapped right in the surface. And then that's just like the tip in a capacitor plate. That's like bringing one of the capacitor plates closer. Therefore, the capacitance goes up. That's what causes this step. This peak is more interesting to us, at least for this talk. That is the signal, we believe, of an electron going onto a dopant. So what I have below here is we parked the bias voltage of the tip right here at 0.05, 50 millivolts, and scanned the tip, moved it around the sample surface to see what happens to the capacitance. If the capacitance went up, then I plot a bright color. If the capacitance goes down, we plot a dark color. And fortunately, happily, what we see is a series of bright dots. If you look at average distance compared to the scan area, well, this bright dot is probably happening because the tip is above a dopant. This is the energy where the electron wants to go on the dopant. We must be doing what we were trying to do in the first place, and to see individual electrons going onto dopant atoms. So, of course, these data made me very, very happy. If we look at the energy, if we probe these different dots, and we probed something like 30 of them, and where this peak occurs, the voltage where this peak occurs, it's directly related to the binding energy. It's simply proportional to the binding energy of the electron going onto the dopant, in this case a hole going onto the dopant. It turns out what we expect the binding energy, as I said earlier, to be about 6 MeV. We do get a histogram with a fairly large width, but it is centered on 6 MeV. So this is more evidence that we're seeing what we wanted to see, and that is the behavior of essentially isolated dopants inside of the semiconductor sample. We can see the charge going onto it, and we can image it in real space. So we got there. If we come here, what I'm going to do is subtract the background from this peak so we can analyze the peak more carefully. We know what the shape of a single electron peak should be, and I didn't spend the time to tell you. It depends on the width, on the magnitude of this excitation voltage. A bigger excitation voltage makes a broader peak. The height depends on the magnitude of the electron charge, which is fixed, and the distance between the tip and the thing that you're trying to measure. As the tip gets farther away, a smaller percentage of the electric field lands onto it, and therefore the magnitude of the peak goes down. And actually what we're seeing here at position A, we see not one but 4 peaks, and we believe the peak that corresponds to the dopant right below position A gives us the taller capacitance peak, single electron peak. But there's also dopants that will tunnel into these other areas that are a little bit farther away. If we go to a higher voltage, we get the electron to tunnel there. It also gives a capacitance peak, but now it's reduced magnitude because the data was taken with the tip here. If the electron's going to tunnel over there, a smaller percentage of the electric field hits it, and that's why the peak is lower. We think we understand that. What I've shown you here is 2 data sets that were taken a long time apart, 16 hours apart from each other, to show you how reproducible the data is. And you'll see it's not perfectly reproducible. Something drifted. The tip got a little bit closer. Actually, I think it drifted out a little bit farther from the surface. But we still see more or less the same structure. I didn't mention, but we do all this without feedback. Unlike STM, there is no feedback to tell you anything about the distance of the tip. It's hard to use feedback when you're doing capacitance. I could talk more about that if you'd like. Here's position B, where we see something different. We see basically a double peak structure, and we think what we have here are 2 dopants, and if we carefully look at this structure, we can extract how far apart the dopants are from each other, even though they're not well resolved, and they're something like 8 nanometers apart from each other. That's still pretty big. 8 nanometers is big compared to the Bohr radius of this sample. We need the dopants, if we really want to see interactions, we need the dopants to be on the order of a Bohr radius. So we need the dopants in this case to be just a few nanometers from each other. So we've looked at this data carefully, and I could tell you more, but I think what I'd like to do is go on to sample number 2, because that's where we really push the dopants close together, and then I can say something more about interactions. So here's sample number 2. It was a gallium-arsenide sample. It had a higher density. It also had lots of dopants within that circle. So as electrons go to many, many different dopants, and the tip can't really see the difference between one and the other because they're all close together compared to its spatial resolution. As we ramp the tip voltage in this case, we see something very different. We don't see one peak or just a few peaks. We see a whole mess of peaks. And of course, when you look at these data, many people say, "You're showing me a bunch of noise." It does look like a bunch of noise. Basically, if you have a random distribution of dopants and they're close to each other, you see a random distribution of peaks. You have lots of interactions, lots of different spacings between different dopants. It's not surprising that their quantum levels are getting shifted in random ways due to all this charge that's sitting around, and everything is random. I'm using the word random too much. But it's not a bunch of noise, actually. If we look at these 2 measurements were taken 8 hours apart, the dashed line versus the solid line, and about 80% of the peaks are showing up in the same place. On the scale of 8 hours, something does change slowly in this sample. Most likely this folklore called DX centers, where charge is metastably trapped and then slowly leaving traps on a scale of several hours, is shifting the peaks a little bit, but more or less the data is reproducible. If we blow up this peak here below the red arrow, there it is. There's 3 different measurements on that peak. We can average those together to get the blue dots. And again, I'll fit it to what we expect a single electron peak to look like. And it's a pretty good fit. So we do believe we're looking at a whole mess of single electrons going into this system. You can ask me, why is the peak asymmetric? And that's because it's a lock-in amplifier, ultimately, that's looking at the output of our charge detector. The lock-in amplifier has this nice thing called the time constant. You can average over the data more and more. As you turn the time constant up, you do pay a price, and this is the tail as the peak gets broader and broader, and it gets broadened asymmetrically. All right, so this was a fairly small voltage range, 0 to 250 millivolts. What if we go over a bigger voltage range? The same sample, we're going to go all the way up to 1.5 volts or so. This data was just a small subset of the total thing that we're ramping over now. We see an overall slope structure. This occurs for essentially the exact same reason as it does in the silicon sample. We can get an accumulation layer forming near the surface. That's a much bigger capacitance, and this gives us this background. On top of the background, though, we see 3 bumps, A, B, and C. And these were quite reproducible. Wherever we went, we saw these 3 big bumps, A, B, and C. The single electrons are way down here. You can't even see them on this plot. Turns out these 3 peaks are something like 15 or 20 electrons all clustered together, giving you this broader structure. We want to wonder, at least, if this has something to do with dopant-dopant interactions, because the dopants are closer together. And that's the question. Can we look at some theory to understand why we would get 3 broad peaks in addition to all these single electron peaks? These end up being the focus of the last, 15 minutes or so of my talk. So we want to understand the broad peaks. Okay, conjecture number 1. Perhaps we have all this mess of dopants below the tip. Perhaps there's about 15 dopants that happen to be relatively far away from their neighbor. If there are 15 dopants that are mostly far away from their neighbors, then they're all going to act more or less the same. They'll act like an isolated dopant. Maybe we have 15 isolated dopants, and what we're seeing in those broad peaks are the first electrons going onto those 15 dopants. They're not all going on exactly the same energy, but they're going on about the same energy, so there's a broad peak due to that. Maybe the second peak is 15 electrons going onto those same dopants, but the second time, etc. So this is the idea. A, B, and C represent the addition spectrum of 15 dopants that just happen to be relatively isolated, so they all act the same way. So with the help of my theory colleagues like Carlo Permarocchi, he sat down, patiently listened to me talk about the data, and said, Stuart, you should think about nearest neighbors, because even though it's complicated, there's lots of randomness going on. If you look at the average distance to nearest neighbor, just statistically, knowing the density of our sample, it turns out to be 4.5 nanometers. The Bohr radius for the sample is fairly large, 7 nanometers. So on average, every dopant does have a nearest neighbor within its Bohr radius. So on average, it's certainly possible to say, well, there's maybe lots of dopants that are coupled to their nearest neighbor. Now it's fair to call them a molecule. So that's why the title of this talk is Donor Molecules. If you do that, then you've changed the charge. Lieb's theorem is okay now. Instead of z equals 1, it's z equals 2. It's 2 protons instead of 1 proton. How many electrons can you fit onto 2 protons? More. Lieb's theorem would say you could fit up to 4, right? 2z plus 1 is equal to 5. So that becomes the new model. In this random network of protons, maybe on average there are 15 or so that happen to be coupled with one nearest neighbor, and they all act about the same way. Therefore, that's how we could explain these broad peaks. The first peak being the first electron going on these molecules. Of course, there could be other clusters with greater numbers of dopants closer together, but these are less likely to behave in the same way. This kind of thing is for example, if we have 4 dopants that are close together, that's going to be a very low energy where the first electron wants to go. If I was an electron sitting here, I'd say that's the first place I want to go. It's the most positive charge. That's the kind of cluster that would explain these very first peaks that we see in the data. These would be later on at a higher voltage where things are giving rise to these effects of peaks A, B, and C. So I really better show you the Hamiltonian. So the way to look at this is a little bit different from what you're used to thinking about. People hear these kinds of experiments and they immediately think, okay, well, the first electron is going to go in the lowest state, the second electron is going to go in the next excited state, the third electron is going in the next highest excited state. And unfortunately, that's not quite right because that's ignoring interactions. A capacitor always wants to see the ground state of the system. If you have interactions going on, the ground state of the two proton system is not the same as the excited state of the, I shouldn't say that way. The ground state of the 2 electron system is not the same as the excited state of the 1 electron system. And here's this formally. The binding energy of the first electron is simply Schrodinger's equation. I'm forgetting about magnetic field right here. So there's the kinetic energy part. There's a potential energy part because we have 2 protons. We have 2 attractive centers. So you can solve this. H on psi is equal to E on psi. That's our eigenenergy there. And the binding energy is just the eigenenergy at the lowest ground state. Now, if we want to add the second electron, we have to make things a little bit more complicated. If you have 2 electrons and you have 2 sources of kinetic energy and 2 sources of potential energy, so here they are, kinetic energy number 1, kinetic energy number 2, potential energy number 1, potential energy number 2, and then here's the interaction. You have to put all this in there. If you don't put the interaction in, it turns out that this case ends up giving you the excited state of the 1 electron case. And you can stare at this for a while to convince yourself of that. But because the interaction is there, this electron will actually go in at an energy that considers the Coulomb repulsion. The fact that the first electron is already sitting there changes the ground state energy to add the second electron. Then the binding energy, or the addition energy, is E2 minus E1, and that's what we actually measure. So Professor Harrison in the chemistry department did just that model, used something called the configuration interaction technique to solve it in an approximate way, but using a technique that's tried and true that should give us results that we can trust. And he made this plot for me. This is the binding energy of the 4 electrons that will go. It turns out 4 electrons will go on there. And this is a function of distance between the 2 donors. So donor number 1, donor number 2 are separated by distance d. They will hold up to 4 electrons. And our experiment, by the way, had an average separation right about here. So epsilon 1, epsilon 2, epsilon 3, epsilon 4 give us the binding energies. Can I put a 5th electron there? No, I can't. Lieb's theorem says I better not do that. Before I show you the data and comparing the model to the data, we add one more thing, and it's very important. Every one of these molecules has its own particle in the box energies, and that's what Professor Harrison calculated. But we also put in the fact that there are other donors that are farther away. Those donors do something. They don't change qualitatively the way that the energies look like for this particle in the box. They won't increase the number of electrons that you can sit over there. This dopant's too far away to do that. But it basically shifts it up and down. The Coulomb attraction or the Coulomb repulsion shifts this box up and down. That ends up being complicated because as we do the measurement, we're adding charges to the system. The ionization, or the number of charges on these non-nearest neighbors, changes as you do the measurement. So it ends up shifting these boxes up and down in a way that ends up being rather subtle. But we do keep track of that and wrote a nice simulation program to do this statistically. What we'll end up measuring in the end is the average addition energy plus all these shifts from all these other atoms that are a bit farther away, shown schematically here. If this doesn't make sense, don't worry, because my cartoon will make sense. Cartoon. So here I'm assuming that we have 3 pairs of dopants, and they're all behaving exactly the same way. So here are our particle in the box, and all the epsilon 1s, epsilon 2, epsilon 3s are lined up with each other. As we then ramp the voltage V tip, there's our chemical potential moving. We see that here 3 electrons go on at exactly the same time until each one of these is totally filled with 4 electrons. Every time that happens, we see a peak in our capacitance measurement, and that's plotted over here. This is obviously a cartoon, and it's quite a horrible approximation to say every one of these pairs of dopants should behave exactly the same way. But if you'll let me do that, I can turn this plot sideways and plot it as capacitance. That's what we actually measure. Charges equal capacitance, and if they all go on at exactly the same energy, we basically have a delta function here, and that's what we would see. Let's make a better model now where we consider randomness. Every dopant molecule has a slightly different distance to its nearest neighbor. That'll shift these a little bit. Moreover, the behavior of other neighbors matters a lot. At the beginning here, we have these two molecules closer together. This one's a bit farther away. That means the electrons want to go here first because there's more protons over here on average. In other words, this positive charge here helps to attract an electron over there. And that's all this cartoon is trying to show you. That's not all. That's one thing this cartoon is trying to show you. The second thing is that these boxes shift up and down as charge ends up getting added to the system. As an electron goes here, now it's partially neutralized this dopant, and that affects this as well. Now an electron's less likely to go over here because one electron already went over here. And you can see it schematically as these boxes shift around. So can we still see anything in the light of all this randomness and all of these chances to smear out our sharp levels? And the answer is yes, we can see something if these smearing effects tend to be small compared to the average distance between our quantum levels in the first place. And if I take this plot and turn it sideways, I'm not going to get delta functions anymore, but I still might get something. Basically, I'll get a histogram. If on average the first electron energy is clustered together, I'll still see something in my measurement. If on average the second electron addition energies are clustered together, I'll still see something. In the schematic, epsilon 3 and epsilon 4 are so close together that they're not well resolved. And of course, I copied the real-life situation. Epsilon 3, epsilon 4 are fairly close together. They're both very weakly bound electrons, and so our measurement doesn't resolve them. That's my conjecture for peaks A, B, and C. So what I'll do next, this is the same data. Actually, I could have said it better. This is the average of measurements that we took at 3 different locations to improve our signal-to-noise ratio a bit. What I'll do next is I'll subtract the black dots from the background curve, the blue curve, and that will just enlarge these signals, and I'll exaggerate the vertical axis a lot so these peaks end up being huge. And then we compare that to the proper theory superimposed right on top, and that's what this is. Here are my black dots, peaks A, B, and C. This careful treatment looking at the configuration interaction calculation, plus all these effects that smear things out, tends to give you this funny structure, electron number 1, electron number 2, electron 3, and 4. Massive approximations were put into generating this theory. The effective mass approximation, or the Luttinger cone approximation in the first place, our treatment of these nearest neighbors, many things were simplified. Yet amazingly, we still get some qualitative agreement between the two. There's no free parameter in terms of the width as far as the fitting goes here, or the height. Our measurement is, in my opinion, amazingly close to what this rather crude theory is predicting. And all the details are not perfect, but I would still propose that we captured the right physics to explain these peaks. So what do I have here? 2 yes molecules? I said all that. All right, I'll just show one more data plot. This is the behavior in a magnetic field. This is just one data set instead of 3, so the signal-to-noise ratio isn't quite so good. There's peaks A, B, and C. As we put on a magnetic field, on average, we see peaks A and B end up going to lower energy. Peak C ends up splitting. This makes us very happy because we were supposing it was 2 different electron peaks in the first place, and this makes that on more firm footing. Amazingly, there's no good theory to compare this to. This is a donor molecule subject to a perpendicular magnetic field. In the literature, there are some high-energy physics sorts of papers where they considered a similar hydrogen molecule, but it's with the field going in the wrong direction. Actually, there's nothing yet really good for us to compare to except for the behavior of isolated dopants. On average, this effect that the magnetic field squeezes the electron closer to the proton tends to lower the energy, and we do see that happening. The first 2 electrons do tend to go in at lower energy. And this effect won't work as well for these last electrons. They're more spread out in the first place anyways. They're much more weakly bound in the first place anyways. So it's not surprising that this squeezing effect doesn't do as much. Rather hand-waving way to deal with the data, but at least I wanted to show you that. So here are my conclusions. I didn't make a really big deal out of this, but these are the first single electron capacitance spectroscopy measurements performed directly with our scanning probe. We use them to look at the addition spectrum of electrons going on to donor atoms and acceptor atoms in silicon and gallium arsenide. For the gallium arsenide work with silicon dopants, the behavior is well explained by considering nearest neighbors as effectively forming donor molecules. Here are our recent papers. The future directions for this work is just what you would expect. It's to do more controlled arrangements of dopants. And we do have some collaborations going now. And hopefully next time I come to talk in a year or so, I can show you lines and pairs of dopants that are controlled in the growth process. So thank you for your attention.